Alright, gonna be recording on my iPad because currently my computer mic is broken, but we're gonna be talking about this nice question. I've not done a video in a while, and I really like this problem, and it's called Frog Traveler, and it is just a good problem because it shows a really common technique used in competitive programming, and yeah, I like the problem. So this question is about graphs. That's to put it vaguely, but I don't even think it's graph theory, to be honest. It's more of like a technique that's used, but it involves graphs, I guess. So what's going on in this question is we we have like a number, right? They give us a number. They give us a number n, and I'm not going to explain it in terms of the storyline. I'm just going to explain it more directly. They give us a number n, and basically what happens is the goal is we try to get n to 0 after some finite set of jumps, right? We try to get n to 0. And the idea here is that in one operation, we can choose to decrease n by 0. So you can decrease, let's say we decrease n by d in one operation, where d is equal to 0 to a sub n. So, for instance, in this test case, n is 10, so you can choose to decrease 10. D would basically be from 0 to a sub 10, which would be 5. The first set of numbers is the a array, second is b. So you can decrease 10 from 0 to 5. So you can choose any d from there. And basically, once you choose that, like let's say we just choose 5, which isn't the optimal scenario, but I'm just showing you what the question is saying. Hold up, give me a second. Hold up. So if you choose to decrease it, then we would be at 5. And then after, anytime you decrease a number, it increases right after. And it basically increases by the b value. So basically, it'll increase by b of 5. So after you do this, it'll increase by b sub 5, which would be 1, 2, 3, 4, 5. So it'd be here, this one right there, the fifth one, right? 1, 2, 3, 4, 5. So it would go back to 10 here. So that's basically the problem. This is what we can condense the problem to. This is pretty good to start off with. Like when they give you like this question was sort of, I had to read it like a couple of times, like maybe 2 or 3 times actually, like understand what it was saying, because unnecessary storyline. But yeah, this is basically what it is, right? You have a number, you're trying to get it to 0. In one operation you can decrease it, but after it increases a little bit, and then you want to find the minimum amount of operations in order to get this number to 0. And you basically have to do some printing at the end, but really minimizing it. Really, like, this printing is like a byproduct of like the actual solution, so you don't have to really worry about that. That's like just like extra, it's just busy work, to be honest. But yeah, they also want you to print, which is, like I said, busy work. Anyways, the approach for this problem is to think about it in terms of like graphs. And it's not too, like, if you have the tags of this problem, like, and if you didn't, I don't think it would really matter, because here's what it is, right? It's not really like, it's just not really it is graphs, but like it's not that special, right? So for example, in this test case, I'll show you the example. We start from 10, right? And basically we know that 10 will decrease anywhere from 0 to a sub 10. So from 0 to 5, right? From 0 to 5, because the last one is 5. And so then we know that after, it can decrease to either 9, it can decrease to 8, it can decrease to 7, it can decrease to 6, or it can decrease to 5. But after, we know the numbers from this have to increase. So for example, if you choose to decrease to 9, you have to increase by b sub 9. B sub 9 is 0 over here. right? 0. So then this would go to 9. And then if you choose to decrease to 8, you have to choose to decrease to 8, you have to choose to increase to a sub b sub 8, which would be 2. So you have to choose to increase to 10. And these other ones are also 10 too. And so obviously in this case, right, there's no point of visiting 10 again, because why would you visit again? You've already visited it again, and in that state, as one might call it, you never even reached 0. So in fact, you don't have to worry about this anymore, because you already know it's a dead end. And this is basically the key observation of the problem. Is just by drawing this out, you can already tell that, like, there's no point of revisiting a state in the problem. If you've already seen that state before, then why revisit it? Why revisit it? And I'll just continue on, but keep that thought in your mind, right? As we make this solution more detailed. So now we have we know that this is the only valid path you would go, because the other ones are just going to go to this or a state that we've already seen, and we know that state doesn't work. It doesn't get us to 0. So if we chose to increase, or technically you don't have to increase, you can increase by 0. But after we chose to increase, we know that we're going to have a bunch of branches now. We'll have, like, we know that from 9 we have to decrease to some value. We decreased you can decrease it by 0 to a sub 9. So that would be by 8. So you can either go here, you can draw the 8, you can decrease it by 8. Actually, here, do this color, right? The blue colors basically are saying that when we travel along that edge, it's going to increase along the edge, and the black one saying it's going to decrease along the edge. Notice, why would I actually draw this out? If you think about it, there's no point of drawing this state out, right? The state in which we have a black edge pointing to 8. Because the idea is that I've already looked at this before. I looked at it up here, and I know that when I looked at it from over there, it just led me to 10, and I never got to 0. So the idea is that, like, why would I connect 8 to that? And similarly, why would I connect 7? Why would I decrease to 6, 5, 4? I already know that they, like, if they already did something, then I would have, if they got to 0, then I would have already been done. I wouldn't even be at this level of the tree if it was already 0. So I know that I don't have to revisit those again, because they're not going to do anything, right? I've already visited that state, so, and obviously that state didn't work if I'm already, like, moving down a depth of the tree. So you know that you only want to look at 4, 3, 2, 1. There's no point of revisiting those other states. And then from here, it's the same idea. You know that you now have to increase the values. And I believe these increase the values to 10. And this increases the value by 1. So this would go to 5. Again, you've already seen these states before, so there's no point of even connecting the edges, because you've already seen the blue state. You've seen that before. You've seen the state in which this indicates that coming from the edge, you're increasing. If you've already seen that state, then there's no point of seeing it again, because you know that if the state would have led to a solution, then earlier up in the tree, you would have already stopped. So this is already, like, feeling like BFS, which is why I'm saying that, like, it's not really too hard to know that this is a graph problem, even though at first it doesn't feel like a graph problem. But yeah, you can already think that this is just BFS, right? However you want to put it. But now we can go here, and now what we can do is from here, we're at the value 5, and we just increase, so we know we have to decrease, and we have some options when we're decreasing. We can decrease from 0 to 5. And basically, you can just connect this 4, 3, 2, 1, and 0. And you obviously know that this is good. If you're at a state which if it's either this or this, it doesn't really matter. As long as the value in the state is 0, then you know that you're successful. And basically, you can the answer for the minimum amount of operations would simply just be the depth of the tree plus 1. So you know that here, it would take, you have to go, this would be 0, so that'd be, this would be 1 edge, and then 2 edge, 3 edge, 4 edge, 5 edge. Wait, what? Oh, five edges, but you don't include the edges in which, basically, the answer here is, I believe, it's just the amount of it's the amount of black edges you have. So it'll be 1. Yeah, it's the amount of black edges you have. That's the answer for the minimum amount of operations, I guess. Or not really. It's just they're asking you, like, basically, you can get the depth of the tree. It would be basically the answer is, if you arrive at 0, it's the depth of the tree plus 2 over 2. That's just like a formulaic thing, but we'll see that later in the code, right? Like, figuring out, like, if you think like this, right, all the details you can just think about when you're coding, right? Like, which is probably bad. You probably should think about it first, but you can see what we're doing here. And what's the time complexity of this? The time complexity of this is actually of n. Like, you can actually solve this in a linear time. In my solution, I got lazy. I used a tree set, so I solved this in n log n, but you can actually do this in of n, because the idea here is, think about it. Since now that I've given you intuition from, like, doing an example, let me, like, formally do this now. So let's define a state. This is a state. Let's say a state, this will be more clear in the code, has a value and it has a move. The value is basically how many feet from the ground it is, or below ground level. And then the move is, do you have to decrease or are you increasing? So, like, in 10, you have to choose to decrease the value. You choose to decrease it to 9, then you have to choose to increase it. Or technically, the increase could be increased by 0. But basically, the move will tell you, are you currently decreasing this value or are you currently increasing this value? So that's what it basically is. And then you basically know that in this problem, there are 2 end states, because the amount of values, they're n values, and either they could increase or decrease. There's only 2 end states, and you basically know that you just have to go through these 2 end states in some order. And at most, the worst case is, like, you have to check all those states. You have to BFS through all those 2 end states, and that would be O of 2n, that would be O of n. And it's basically going to be pretty clear. So I will show you this in the code. This is basically, like, you only have to BFS through these 2 end states, and right now that's pretty vague, but I'll show you in the code. I think it's a good time to show the code now. So here you have a state which this is actually kind of there's some things in my code that are unnecessary. Like, when I coded the state class, I thought I needed to sort by the value, but this is unnecessary. Anyways, the visited is to not revisit states. Remember, you don't want to revisit states like we showed in the example. Why would I revisit a state? There's no point of revisiting a state. Think about it. You're trying to minimize the amount of operations, which is equivalent to minimizing the depth. If you're looking at a state, if you're going to revisit a state and you're using BFS, that means at a further depth, you're revisiting the state again. So why would you? That's unoptimal. You're revisiting the state when it's gonna just lead to more operations involved. So this obviously is just obvious, right? I think it's extremely obvious at this point. Now the first thing I'm gonna do is I'm going to have a tree set. You don't need a tree set, but whatever you have, it doesn't really matter at this point. You basically add all the possible increased states, right? These are all the possible increased states. And then you have a queue, and this is gonna hold the, like, current states, and then you have a parent. This is basically to print out the path, don't worry about it. here's the thing, right? You push in the start state. The start state is pretty easy. The start state is gonna just be where did I define the start state? Well, where is the start state? The start state is just n. Oh, here it is. So you know that the first state is that you're gonna start at n and you have to decrease. Basically, you know that this is the current state. You're gonna get the move, right? And you're gonna visit the state to make sure that you don't have to revisit. If the current state value is 0, then you can put the ending state is the current state. Oh, this is just to print out the path, don't worry about it. But if the current state value is 0, then we're done. We can get out of the loop. Now we have to consider cases. If we're in a decrease state, then we know from here, the only way you can transition is if you just finish decreasing a value, you have to increase a value afterwards. Like we showed in the example in the tree. You're at a state, you're always increasing a value, then right after you increase value, you have to decrease it. So you can only if you're in a decrease state, you can only transition to increase states. Which increase state should be transition to is the question. This is the optimization that makes the solution of BFS work. The optimization is that there are only n possible increase states. Right? You can either you can basically or yeah there or yeah if you we can only transition to increase states basically. Oh yeah, because so basically there are n possible increase states, right? Like if you have a value 10 and you know that 10 is a decrease state, then let's say 10 is a decrease state, then 10 is a decrease state, then you can transition to like an increase state 9, and the increase state means that like the value is about to increase after you like move another edge. So you know that there are only n possible increase states. You can either have an increase state where the value is 0 and you increase it, then you have to increase it after you attach another edge when you transition from there, and there are only n possible ones. And the idea here is that you never have to revisit a state again. So the idea is that the motorized complexity, you have to only visit a total of n increase states at worst case, right? You basically know that after you get the increase state, so increase states out first, this is the reason why you go from the biggest to least is because this condition has to be true. This condition is that this is basically saying that like if you have 10, you can only decrease it by 5. So you know that like 10 minus 5 has to be less than or equal to 5. And but you put the biggest ones first because obviously those are gonna work quicker. And so once it doesn't work, you don't have to check the rest of them because you know that like the else break, you know that they won't work. So you put this child in the states. If you have not visited the state, then you put the state, you add the child to it, and then basically you keep track of the parent the parent state. This is just to print out the path, don't really worry about it. It's to print out the path. But the idea is that for the increase state, you're going to remove the child. The idea is that this is the solution. It's basically saying that, okay, anytime I'm in a decrease state and I'm trying to transition to any more increase states, then I know that like I won't have to revisit them again, right? So you don't have to check them. You don't have to constantly go through your while loop and check the ones, because you know that those increase states will be already visited that, but you don't want to go to your while loop and already like you have to check them, right? So just remove it, get them out of here, and then it optimizes this. So this is really the main solution. And then the other case where you're transitioning to a decrease state, it's pretty easy. You just simulate the problem, and then you keep track of the parent. So this is the child, and keep track of its parent state, And then if the ending state value is -1, this is basically meaning that this ending state we never got here. If it's -1, print out -1. If it's not, just print out the path. And this is basically this is like, if you have not done BFS, I recommend you do like BFS problems, like introduction to it. But this is basically just a common way to get the path. You know, you just keep track of the parent, and then you like go backwards, and then you just reverse it. It's pretty self-explanatory if you've done it before. And then you print out the minimum number of moves, which is just the path.size plus 1 over 2. Remember in our solution, it was just the number of black edges, because they don't want you to, they only want to ask you how many times did you have to decrease the value. That's basically what they're minimizing, the amount of times you have to decrease the value. You have to decrease stuff, basically. So you have to decrease it by path.size plus 1 over 2. The reason why it's a ceiling, this is basically equivalent to the ceiling, is because you start with having to decrease the value. And then afterwards, you print out the path. This is just to make sure that you don't print out, the other ones, right? Because you only want to print out the amount of times it decreased, right? Which is this. But yeah, afterwards, and that's the solution. Basically, it is just thinking about, it's basically just thinking about, you don't have to revisit a state, right? This removing line, like if you don't put this removing line, then this entire line speeds up the entire algorithm. So it's really just that one observation, and then it's just BFS. So yeah.